Hello, welcome back. Continuing from where we left off, we are looking at taking the second dissociation constant of phosphoric acid, and that's the equation we have written right here. Okay, so we'll just continue from this point and we'll say writing out this exclusively using water as the other reactant as it reacts in solution, you have, so we are taking from point number 2, adding water as aqueous reactant. So we have H2PO4 minus plus water, equilibrium forward and backward reaction, and we have H3O plus donating a phosphoric acid donating a proton, and what you have left is your HPO4 2 minus. All right, now in this case this is acting as an acid because it's donating a proton, so this is acting as an acid because it's donating a proton, and of course this is acting, the water here is acting as a base, so it's acting as a base, because it accepts a proton, and this product here is what we refer to as what? The conjugate base. This is referred to as the conjugate base. And what is the conjugate base actually? It is what is produced at the end of the reaction. So at the end of this reaction, what we have produced here outside the proton that is here, we have the conjugate base. So we can just write what is produced at the end of the reaction. So the whole of this here is actually the conjugate base. So what is important here is what is giving up the proton, which is acting as the acid right here, and what is taking the proton, as what is giving up the H plus and what is taking it. So the giver here is H2PO4 minus and the taker is water. So the giver is the acid and the taker is the base. So you can as well say the donor is the acid and the acceptor is the base. Okay, so that's basically for weak acid. We want to quickly introduce weak bases. What does weak basis look like? Weak basis. So weak basis. So what's a base? A base, whether weak or strong, is something that produces hydroxy ion in solution. Okay, so strong basis produces hydroxy ion directly. So by directly, it means it dissociates completely, and when it dissociates, OH goes into the solution. That's for strong base. So let's quickly take that down. A base, whether weak or strong, is something that produces OH minus, which is your hydroxy ion in solution. All right. So you have strong base produces OH minus directly. So you have strong base. It produces OH produces OH ion directly, okay, and they produces OH directly, okay, and what that means is that it dissociates completely, and when it dissociates, it goes into what? Solution. So in the next slide, we'll look at example of a strong base. So I just take the next slide. So example of a strong base will be example so we have potassium hydroxide. So when this dissociates, it produces potassium ion plus hydroxide ion. So it's a base because it produces hydroxy ion directly. Note here that there is no equilibrium here. It is complete dissociation. There is no KOH left. It is just the K plus and the OH minus floating around in solution, just like we saw with the strong acid. So you can simply indicate this here that no equilibrium is found here. No equilibrium, no equilibrium is found here. All right, it is what you have is a complete dissociation. It is a complete dissociation here, and that means there is no KOH left after the reaction. What you have is just the K plus and OH minus floating around in solution. So thus, if a strong base produces hydroxy ion directly, therefore means a weak base produces hydroxy ion indirectly. Therefore, or thus, a weak base, which is our focus, a weak base produces hydroxide ion. A weak base produces hydroxide ion indirectly. Okay, so let's look at an example of a weak base. Example here, we have a reaction. Example of a weak base we want to look at. Let's look at ammonia, NH3. Okay, ammonia, when put into water, note that water here is acting as an acid, and I've written it as HOH, the same thing as H2O. Okay, so it's reacting as water, When that reacts, you have the forward and the backward reaction, and what you have is ammonium ion and OH minus. OH that it produces is what indicates it as a base in the first place, and it's a weak base because it is producing the hydrogen ion indirectly. It has been done indirectly. Here you have the ammonia here acting as a base. Why? Because it is the one that is accepting the proton, while the water here is actually acting as the acid, because it's the one donating the proton. So the hydroxide ion in this reaction has been produced in the solution. However, it has been done indirectly. So the hydroxide ion has been produced in the solution okay. However, it has been done indirectly. Okay, so worthy of note is that we look at that in the next slide. So I want to note down something here. So worthy of note here is that note a weak base is something that actually extracts an hydrogen ion from water to leave hydrogen ion behind, as seen in the reaction above, as the reaction in the previous slides. So let's take this important note down here. A weak base is something that actually extracts an hydrogen ion. Okay, it extracts it from water, and because it extracts it, that's why it is a base. To leave the hydroxide ion behind, it extracts hydrogen ion H plus to leave the hydroxide ion behind, as seen in the reaction above, or the previous reaction, as this case may be. So the generic reaction for this weak base reaction is as follows. The generic reaction for this is as follows. So you have B plus water. Okay, now the B that is acting as a base extracts hydrogen ion from water to be BH plus, while leaving hydroxide ion in the solution to float around. So here you say where B represents any weak base. Here B represents any weak base or anything that behaves like a weak base, or anything that behaves like a weak base, that behaves like a weak base. So rewriting the reaction above, that's that ammonia reaction, we can write an equilibrium expression for it as follows. So I want to do that in another color. Let me take purple. Right, so the previous reaction where we showed ammonia reacting with water, so rewriting the reaction to write an equilibrium, we have NH3 plus water HOH forming ammonium ion plus OH minus. So equilibrium constant reaction for this will be the concentration of ammonium ion and hydroxy ion divided by the concentration of ammonia. And that, instead of giving you acid dissociation constant, it gives you Kb, which implies the base constant or base association constant. So this implies the base constant or the base association constant. Great. So that's the equilibrium reaction for this. In the next slide, we'll be looking at an example of a weak base. Okay, so we want to look at example of a weak base, and we'll say this is example 3. So we say pyrimidine or pyridine is a weak base. All right, so we have pyridine is a weak base. That's the structure here. Okay. Okay, that's it. So this is a weak base. Now, when pyridine reacts or puts in water, what you have, forward and backward reaction, is pyridine H plus your OH minus. Note that the pH will still be above 7 from the neutral pH. So what you have, if we are to write the equilibrium constant here, is your Kb is equal to concentration pyrimidine H plus and OH minus, okay, divided by concentration pyridine. And that gives a concentration constant of 1.7 times 10 raised to power minus 9. Again, this is a very small number, which shows that the reaction have not gone very far forward, as most of the reactants are still in the form of pyrimidine. So this is a very It's a very small number, which shows that have not gone very far forward, as most of the reactants are still in the form of pyridine. So it is worthy of explanation here that when a species has an hydrogen plus, which is a proton, it can give up. It can give up. It is in its acid form. Then when it can accept an hydrogen ion, it is in its base form. Thus, the form of whether it is an acid or a base is not absolute. It depends on its behavior, whether it is behaving as an acid or a base. Again, in science, we need a point of reference from which to measure something. So we want to note how we see an acid behavior or a base behavior. So we write here, note when a species has a proton, it can give up. When a species has a proton, it can give up. It is in its base form. Sorry, give up, it is in its acid form. I beg your pardon. Okay, it's in its acid form. When it can accept an hydrogen ion, okay, when it can accept an hydrogen ion, it can accept a hydrogen ion. Okay. Okay. All right. So when it can accept a hydrogen ion, it is in its base form. Acceptance, base form. Okay. So whether the form of whether it is an acid or a base, it is not absolute. Thus, form of whether it is an acid or base is not absolute. It's not absolute. It depends. It depends on its behavior. It depends on its behavior. Very key. Whether it is behaving as an acid or a base. So we look at another slide. In science, we need a point of reference. Points of reference. In science, we need a point of reference from which we can measure something. We need a point of reference from which to measure something. So as an example, so what is important here is the perspective. So we want to look at some example. Okay, so example, we have NH3 and we have NH4 plus. Okay, then we have NH4Cl. So what we have here, this is a base because it's accepting a proton, and this is what? An acid. Okay, now we have HF, hydrofluoric acid, and we have F minus. Now this is what? An acid, because it's giving off its hydrogen, and this is what? A base. And what we have here is Na fluoride. So if we look at all of these, it's what is important is your perspective of what is accepting a proton or what is giving up a proton. So what is important here? What is important here in this example is the perspective. What is important here is the perspective. The perspective is what is important here. So you can also have a reaction like your Ha plus water, and we have a forward and a backward reaction forming H3O plus A minus. And what this signifies is what? An acid reaction. And what we have, the A minus again can also react with water, and that will give you another form of reaction where A is accepting the proton, okay, and leaving what? The OH behind, and that implies what? A base reaction. Also, you have the idea of Ka and Kb. When a species is behaving as an acid, you have Ka, which is the dissociation constant, and when a species is behaving as a base, you have Kb. There is actually a relationship between these two, as we'll see in the next slide. We have Ka and Kb relationship. So when a species or a species is behaving, a species is behaving as an acid, it implies is an acid dissociation constant. And when a species is behaving as a base, it implies Kb, which is your base association constant or base constant. Now, there is a relationship, okay? There is a relationship between the two, between Ka and Kb, as follows. So the Ka Kb is actually equal to Kw, and that is equal to 10 raised to power minus 14. So using hydrofluoric acid, as an example, you have HF, alright, plus water, forward, backward reaction, weak acid, H3O plus F minus, and you have Ka is equals to 7.2 times 10 raised to power minus 4. You could recall this. Alright, then you have F, this fluoride now goes into the reaction acting as what? A base, because it's going to attract or withdraw a proton to form HF, leaving OH minus. And what that implies is what? A base constant, because it's a base reaction, as it is acting what? As a base. Now, the relationship between Ka and Kb is that you have Kb here. To get Kb from this relationship, okay, you simply, from that reaction, say Kb is therefore equals to Kw divided by Ka. And this implies the relationship. This implies this is the relationship. Great. Thank you for staying with me till this time. We'll continue on this series from the next lecture. Thank you.